welcome to the Explainer. Today we're going to crack the code on what is, let's be honest, the most famous equation in all of science. But here's the thing. This isn't just a bunch of symbols on a blockboard. No, this is, well, it's kind of like the operating system for our entire universe.
All right, so let's start with something you might find a little surprising. This equation. It's woven directly into our daily lives, and a lot of the time we don't even notice it's there. I mean, seriously, think about it for a second. That GPS in your phone, it absolutely has to account for relativity, or it would be off by miles every single day. And what about the sunlight that's, warming our planet and powering pretty much all life? Yep, that too. This isn't just some abstract physics problem, it's the invisible engine running our modern world. Okay, but before we dive any deeper, we need to clear up a huge misconception. I'm sure you've heard this one. As things get closer to the speed of light, they get heavier, right? It's a super common way to explain it, but it's not really the full story. The actual reality is something way more profound. So here it is. The real kind of mind-bending idea at the very heart of this equation is that energy and mass, well, they aren't separate things at all. They're just two sides of the same universal coin. And today, we are going to walk through exactly how we know that's true. Okay, so let's dive right in. If we really want to understand E equals mc², we first have to get our heads around a pretty wild concept. What happens to things when they get pushed to the universe's ultimate speed limit? So, in our normal, slow-moving world, momentum is pretty simple. Just think of billiard balls hitting each other. Totally predictable. But as you get an object closer and closer to the speed of light, something really weird starts to happen. Its resistance to acceleration just keeps going up. It's not that it's magically getting more stuff inside it. It's that if you give it a push, you get less and less of a speed boost in return. It just gets harder and harder to make it go faster. Okay, so the big question is, how do we get from that strange idea all the way to E equals mc²? Well, it's not some random guess Einstein just pulled out of a hat. It's an absolutely inevitable conclusion. And the best part? We can prove it using a brilliant and actually surprisingly simple thought experiment. So let's just walk through it together, step by step. To get started, we only need to agree on two things. These are the absolute bedrock of Einstein's special relativity. First, the laws of physics are the same for everyone, everywhere. Doesn't matter if you're standing still or flying in a spaceship. And second, and this is the one that really messes with your head, the speed of light in a vacuum is constant for everyone, no matter how fast they're moving. Okay, let's build this thought experiment. I want you to imagine you're inside a spaceship, and you've got this perfect clock. How it works is it shoots a little pulse of light from the floor, it bounces off a mirror on the ceiling, and comes back down. Tick, tock. From where you're sitting, inside the ship, that light is just traveling a simple straight line, up and down, right? Super simple. All right, but now let's switch things up. Imagine someone is standing on a planet watching your ship fly by really fast. What do they see? Well, because the ship is moving forward, they don't see that light pulse go straight up and down. No, from their perspective, the light has to travel a longer diagonal path. It has to go up, but also forward just to catch up with that moving mirror. And right there, that is the absolute core of this entire proof. You've got the vertical path of the light, the horizontal path of the moving ship, and that diagonal path the outside observer sees. What do you get? A perfect right triangle. And this simple shape from grade school math is the key that unlocks everything else. That's right, it's the Pythagorean theorem, a² plus b² equals c². This gives us the exact relationship between all those distances. The vertical distance squared plus the horizontal distance squared equals that diagonal distance squared. It's this beautiful, simple piece of geometry that connects the ship's speed with the constant speed of light. So what does this little triangle actually tell us? Well, think about it. We already agreed that the speed of light is the same for everyone. But the outside observer sees the light travel a longer path. So if the speed is the same, but the distance is longer, what's the only possible conclusion? For them, time itself must be passing more slowly inside that moving ship. And when you do a little bit of algebra on that triangle, you get this first equation for what we call time dilation. Now here's the really crucial link. If time is slowing down for that moving object, then for all the other laws of physics, like momentum, to still work properly for everyone, something else has to change to balance things out. And that something is its resistance to acceleration, what we call its relativistic mass. and it has to increase by the exact same factor. That's where we get our second equation.
Okay, so what does this all have to do with energy? Well, the extra energy an object has when it's moving, its kinetic energy, it's not just about speed anymore. It turns out that energy is exactly this increase in its relativistic mass, just multiplied by a massive number, c². You can think of it this way. The energy of motion is literally being stored as extra mass.
And this brings us to the final, absolutely brilliant step. Einstein thought, okay, if the energy of motion is stored as extra mass, what about the mass an object has when it's just sitting still? And he realized that this rest mass must also be a form of energy. So, with a simple rearrangement of that formula, we land on the most elegant, powerful, and universe-altering equation ever written. An object's total energy, E, is equal to its total mass, m, times the speed of light squared. E equals mc².
So the big takeaway here is this. Mass isn't just stuff. It's not just a lump of matter. Mass is an unbelievably concentrated, kind of crystallized form of energy. They are, for all intents and purposes, the same thing.
And look, this isn't just some crazy math on a chalkboard. We see this conversion happening all around us, all the time. It is the reason the sun shines. Every single second, the sun converts about 4 million tons of its own mass directly into the light and heat that makes life on Earth possible. It's the powerhouse behind nuclear reactors. It's even used in medical PET scans to literally see inside the human body. Mass becomes energy, and energy becomes mass every single day.
And once you grasp that, this one simple equation completely changes how we look at the entire cosmos. It really is the key to everything.
I mean, the entire history and the structure of our universe, it all comes down to this. From the Big Bang, where pure energy cooled and condensed into the first particles of matter, all the way to the insane gravity of black holes, everything is governed by this fundamental truth that mass and energy are equivalent.
So, what it really teaches us is that the universe isn't made of two separate things, matter and energy. It's actually made of one single, dynamic, interchangeable entity. That is the beautiful, unified picture of reality that Einstein gave to the world. Understanding this deep connection, it unlocked the nuclear age. It completely transformed the 20th century. So the question for us now, as we look ahead to the future, is pretty simple. What new frontiers will this fundamental truth allow us to explore next?